Logarithmic, exponential, and other transcendental functions. So in this video, we're gonna primarily state results. We're not gonna show the majority of them. We're gonna only adopt the results, and we're gonna employ them in some problems. With that said, obviously, whenever you want me to discuss with you, or if you want me to record a video on the proofs of the result, I'll be very happy to do so. Just contact me. All right, so we're gonna start this section by revisiting, not in great details, inverse functions. We're gonna have a crash course on this, but if you want more details on that, I have a video on this. Okay, so just go to the channel, and the video is entitled Inverse Functions. And also we're gonna talk here about their derivatives. So what's an inverse function? If you have a function f that goes from a to b, we say that g is its inverse that goes to b, from b to a, provided we have the following. If you compose the two in any order, right? If you compose the two in any order, we have neutral action, which means if you plug in an x in this function, in this composite function, you get the x back, and this is for any x. X goes to f first, so it has to live in a, right, in the domain of the function f. So x has to be in a, and if you compose them in the other order, then you also get x, and this is for any x now in b. Why? Because x is going to g, and as such it has to be accepted by g, so x has to live in the domain of g. Okay, so if these two are verified, then we say that g is an inverse of f. Correct? So we say that g is an inverse of f. And here I said an inverse. It's just a definition. This is just a definition, right? And that n actually turns out to be unique. Okay, again, it's in the video if you want the details. But an inverse, when it exists, is unique, right? Okay, let's keep that crash course going. What I want to say now is that what are those functions that have inverses? So you also know the following result. Let me just state it. Every one-to-one function. What's a one-to-one function again? A one-to-one function is a function that verifies the following. F of x1 equals f of x2, if we're talking about f being that function, is equivalent to saying that x1 is equal to x2, right? This is what one-to-one means, one-to-one function means, right? So this is what this means. If you want to verbalize this, this means that no element in the range of the function is the image of more than one element in the domain, right? Or equivalently, you can say no two distinct element of the domain of the function have the same image. Okay, so one-to-one functions are those functions which are characterized geometrically by having their graph passing the horizontal line test, if you remember, right? So the horizontal line test says if the graph of the function doesn't cross any horizontal line more than once, then the function is one-to-one. Okay, so this would be the geometric characterization of this algebraic property. Okay, all right, so from that course or from that video, we know that every one-to-one function has an inverse. Okay, and the inverse, when it exists, is unique. This is another thing that we know. an inverse of a function when it exists is unique. Again, if you want to see the proof of this, please visit the video. Because of this result here, so we have this result, and because of this last one, if f is the function, so the inverse of such a function is, since it's unique, it has a notation. So the inverse of f is denoted by f inverse, right, like this. Correct? Again, I'm just revisiting some of the concepts that you know. And the very last thing I need here, probably second to last, how are the graph of f and f inverse related? So they are related, they are symmetric to each other with respect to the line y equals x, right? The line that bisects the first and third quadrants, correct? So this is how the two functions are intertwined, the two graphs are intertwined. And the very last result, probably I should have said it before, it stems directly from the definition here, is the following. If f of x is equal to y, that's equivalent to f inverse of y is equal to x, correct? So if f takes x to y, f inverse is gonna undo the action. It's gonna take you back from y to x. Okay. All right. So these are the primary ingredients that I need from that concept. Now we're ready to state the theorem. Again, if you would like to see the proof, I'll be very happy to do it, but you have to contact me and I'll record a video for this. So the theorem reads as follows. If you have a one-to-one and differentiable function, so if f is one-to-one, so its graph passes the horizontal line test if you want to start imagining it geometrically, it's differentiable, so it doesn't have any kind of corners or kinks or discontinuity, right? So if f is such a thing, with inverse function f inverse, like this, and this number, whatever this number is, it's not zero. This is the derivative function evaluated at the pre-image of a under f. Okay, so it's f inverse of a. Okay, and what's f inverse of a? What's f inverse of a? F inverse of something is a number so that f of that number is a, right? So if you replace y by a, you read it as follows. F inverse of a is a number x, so that if f applies to x, if f acts on x, you get back that number a. Okay, so if under these hypotheses, then you get the following. You get that the inverse function, f inverse, is also differentiable at this number a, and moreover, its derivative, the derivative of what? The derivative of the inverse function at the point a, so not only it's differentiable at a, we also know its recipe. The derivative of the inverse function f at a is equal to the reciprocal of that number. The derivative of f at the point f inverse of a. Okay. Look, the proof of this is not hard, but again, let me just give you not a proof, but at least something that makes you believe it. Okay. Look, if you know a priori that the function is differentiable, the theorem is stronger than this. The theorem tells you that the function inverse is, or the inverse function is differentiable at a. Let's put some more conditions on the hypothesis of this theorem. Let's say that if we know that the inverse function is differentiable at a, so if we know that this number exists, what can we do? We can do the following. What can you say then? F inverse composed with f at a. Okay, at x, let's take it first. What is this? This is x, correct? This is x. Why? Because if you remember by definition, if you compose the inverse function and the function itself in any order, you get back, I mean, you get neutral action, right? So whatever you plug in, you get it back. So we know this, right? And now if you differentiate this, let's say you use implicit differentiation. If you differentiate with respect to x both sides, what do you get? You get the left hand side, you can use chain rule. You can use chain rule and get f inverse, right? F inverse prime at this number, f of x. So the derivative of f with respect to f of x times f prime of x, correct? Chain rule is equal to 1. Do you agree with me? Because the derivative of x with respect to x is 1. So you get this, right? And now if you know that this number is not 0, you can divide by this number. And as such, you get the derivative of the inverse function at the point f of x is equal to 1 over f prime of x. Correct? So you get this. And now if you call f of x to be a number a, if you call f of x to be a number a, so what's x? If f of x is a, what's x? If f of x is y, then x is f inverse of y, right? So if f of x is called a, then f inverse of a is gonna be x, right? So who's x then? It's gonna be f inverse of a, and you get this formula, right? I mean, you get the derivative of the inverse function at a, that's this side, is equal to 1 over f prime at this number x, which is f inverse of a. Correct? This is not the proof of this again, because the theorem says that the inverse function is differentiable at a, and here we're starting from the fact that it's differentiable, so I assume that it's differentiable. I weaken the theorem in some sense. Okay, but I made this little discussion just to kind of make you believe that. Okay, the proof itself, as I mentioned, is not hard, but I'm skipping it just for the sake of this video, but if you insist in doing it, I'll be very happy to do it for you. Okay. All right, so we have the result in black here, and let's see it in action. Let's take this example. If f of x is equal to x squared, well, this function is not 1-to-1. However, you restrict it on 0-2, correct? You restrict it on 0-2, it becomes 1-to-1. How do you graph this function? How do you graph this function, f of x? Well, it's something like this, right? It's a piece of the parabola between 0 and 2. Yes? So it's this part of the function y equals x squared. And certainly this is 1-to-1. It's continuously monotonic, right? It's continuously monotonic. It passes the horizontal line test. Okay? Find the derivative of the inverse function, because this function is 1-to-1. Every 1-to-1 function has an inverse. So for that inverse, differentiate that inverse and find it and evaluate it at 1. Okay? So based on this recipe, based on this theorem that we just talked about, well, the function f is x squared. The inverse function, you don't even need to know what the inverse function here is. I mean, even though it's not that hard to find it, but you don't even need to go through the trouble of finding what the inverse function is. You can just, according to this, you can differentiate it at, differentiate that function at the desired point. Okay. All right. So according to that theorem, what can we say? We know by the previous theorem we have that f inverse prime, so the derivative of f inverse at the point 1 is equal to 1 divided by the derivative of the function f itself at the point f inverse of 1. right? What did I do? I copied this. Okay, I didn't do anything. All right. And the question is, what's f inverse of 1? What's f inverse of 1? What's that guy? What's this guy? What is this guy? Well, what am I looking at? I'm looking at a point. This is the function f, right? I'm looking at a point. Let's give it a name. How about b for a name? Okay. So I'm looking at a point whose image under f is 1, correct? So one more time. What does this mean? What does this mean? So let's talk about it here. What does f inverse of 1 mean? If you call it b, right? If you call it b based on the previous page, based on this, f inverse of 1, so y is 1 and x is b, correct? In our discussion, f inverse of 1 is equal to b. This means f of b is equal to 1, right? That's what it means. So f of b, saying f inverse of 1 is b, that's the same thing. That's the same thing as saying f of b is equal to 1. All right? So I'm going to take that with me and this knowledge with me and just rewrite it. So that's the same thing as saying that f of b is equal to 1. Make sense? So I'm looking at a point here, questioning what that thing is, whose image under f is 1. That's the b. That's the b here, right? That's the b here. That's the b. Okay. It's not hard to see that b should be what? Should be 1, right? Let's discover this again. This is the same thing as saying f of b. What's f of b here? Is x squared. F of x is x squared, so f of b is b squared is equal to 1. And that's the same thing as saying that b is plus or minus 1. But don't forget, our b should be part of the domain of the function f. Our b should be part of the domain of f. So it's just the positive part, because the negative part is not part of the domain. Agree? So I'm gonna circle just the positive part to indicate that this is the only choice that we chose, and the reason is because b is in the domain of the function. D sub f for domain. Okay. All right. So now I know what this guy is. I know what b is. It's actually 1, right? So I get that this is equal to 1 divided by f prime of the b, which is 1. This one is not that purple one here, okay? How about I write it in a different color just to highlight for you that they're not the same. Let's write it in red. They're not the same. This one is not that one. It's the b, right? It's the b. And the b was plus 1. Okay? All right, just to be very clear here, all this package was needed to transition from this stage to this stage, right? Okay, and now we're almost done. I need to find f prime. I need to find f prime, the derivative of this function f, and then evaluate it at 1, and then we're done. Okay, so let's do that. What's the derivative of the function f? Well, the derivative of this function is 2x, right? So that's 2x. And then what can you say about the derivative of f at 1? So now you know what the derivative function is at any point. Now you want to evaluate it at 1. What's f prime of 1? If f prime of anything is twice the thing, f prime of 1 is simply 2, right? It's simply 2. And then, so the denominator is 2, right? The denominator is 2 then. So that whole thing is 1/2. Okay. All right. So the derivative of the inverse function at the point 1 is 1/2. Let me show you a different way to do it Without going through that theorem, remember, this theorem allows you to differentiate the inverse function at any point, to find the derivative of the function f inverse at any point without finding the function inverse at all, right? We didn't find the inverse function, right? So it's a powerful theorem. It allows us to differentiate the inverse function at any point without even knowing what that inverse function is. All right. In this case, the inverse function is not hard to be found, right? It's, what is it? It's the square root of x, correct? It's not hard to be found. As such, let's use that angle and find the inverse function at 1, the derivative of that inverse function at 1. So a different approach. So let me see here. Alternatively, we may find f inverse first, right? The recipe of f inverse first, and then differentiate the function f inverse, right? And evaluated at 1, because that's what we want. We want to find the derivative of the inverse function at 1. So what we're gonna do is we're gonna find f inverse in the second approach. We're gonna find f inverse, we're gonna differentiate it, and then evaluate it at 1. Okay, so what's f inverse here? It's the square root. Remember how you find the f inverse? You call this guy y and you solve for x, right? So x is gonna be plus or minus the square root of y, but x is positive. Oh, where is it? It's here. X is positive, so it's gonna be the plus square root. Make sense? So if f of x is equal to x squared, if you call this y, that's equivalent to saying that x is plus or minus square root of y. But again, we're gonna talk about plus. We're gonna accept the plus, reject the minus, because x, it's the x that I'm choosing to be positive square root of y. Since x is bigger than or equal to 0, it's certainly the positive side, right? So because x is bigger than or equal to 0, I'm gonna choose the positive sign, and then x is plus square root of y, right? So that's the inverse function. So that is to say, the inverse function of x is equal to square root of x, right? Okay. And now I can differentiate that function. What's the derivative of this function, which is square root of x? It's 1 over twice square root of x, right? Just use the power rule for this, x to the power half. Okay, so you get this, which means if you want to evaluate that function, that derivative function, at the point 1, you just have to replace x by 1, right? Because this is f inverse, the function f inverse prime. If you want, this is at any x. If you want to evaluate that function at 1, plug in 1 here, so that x is going to be 1. So that's going to be 1 over 2 square root of 1, which is 1 over 2, right? Agree with me? Mm-hmm. Which is exactly as we found above. That's the same thing as we found above, obviously. But I hope you understand the differences between the two approaches. The first approach, we used the theorem. We didn't even find the inverse function. We differentiated it without even understanding what this inverse function is. This is why this theorem is powerful. It allows us to bypass the rest to find the recipe of the inverse function. And the other one, we went in a very direct, the more direct approach is that, okay, find f inverse, which is not hard to be found here, and then differentiate it and then evaluate it. Okay? All right, so next, let's do the next one. So let f of x to be twice x plus cosine of x. find the derivative of the inverse function at 1. So in this context, the inverse function is hard to be found, right? It's hard to find the inverse function in this context. However, we're gonna, according to the previous theorem, we may be able to find the derivative of that function even without knowing it at the point 1. Okay? All right, in order to actually use that theorem, we have to verify it as we did before. We need to check that the function is one-to-one, and we need to make sure that the function is differentiable. And we need to know that this guy is not 0, correct? So, 3 things. Why the function is one-to-one? In the previous context, it was easy, right? It was, I mean, we know how to graph it, and it was differentiable because it's a polynomial, and it turns out that this guy is not 0. It turned out to be 2 at the time, right? It's not 0, so that's why we were able to use it. Over here, so we need to make sure that the function, so we need to make sure that f is one-to-one. That's number 1 thing. We need to make the case. We need to check that the function is differentiable. That differentiability is easy, right? Differentiability is immediate. F is differentiable everywhere on all of R, correct? Because it's a sum of a polynomial and cosine of x. Each one of them is differentiable on all of R. So as such, the sum is going to be differentiable on all of R, right? The sum of 2 differentiable functions on an interval is differentiable as well. And f is the sum of these 2 differentiable functions everywhere. All right, so f is differentiable on all of R, easy. So why f is one-to-one? Why f is one-to-one? Well, how about we show that its graph passes the horizontal line test. And the way we're going to do it, we're going to show that the function is continuously monotonic. So on R, right? By being continuously monotonic, what do I mean by continuously monotonic? It's continuous and it's either always increasing or always decreasing, right? If a function is continuously increasing, then it certainly passes the horizontal line test. As such, it's going to be one-to-one. And if it's continuously decreasing, it's going to also pass the horizontal line test. So what I'm going to do is I'm going to show that it's continuously monotonic. Certainly f is continuous, right? Because it's differentiable on all of R. So f is continuous on R, right? Differentiability is a stronger statement, stronger concept, stronger notion than continuity, in the sense that every differentiable function is itself continuous. One-to-one, it only remains to show that the function is monotonic. So how about finding what the derivative of the function is and check its sign? What's f prime of x? What's the derivative of this function? Well, the derivative of this function is 2 minus sine of x, right? The derivative of 2x is 2. The derivative of cosine is negative sine. And what can you say here? What can you say? Sine of x, the worst it gets, or the best it gets, is 1, right? So 2 minus the best it gets is going to be the least that derivative is going to get to, right? This is always bigger than or equal to 1. Do you agree with me? Because sine of x, the best it gets is at 1. So 2 minus something that gets at most to 1 is something that gets at least to 1. And this is a positive number for all x and r, right? For all real numbers, right? For all real numbers x. So what can you say then? What can we say then? So f prime is continuously increasing. Let me use this for increasing. So f is continuously increasing on R. As such, f is not f prime, I mean f here, right? F is continuously increasing on R. So as such, f is one-to-one on R, right? Okay, so the function is one-to-one and it's differentiable. And what else? I still have to check that this is not 0, right? Let me take you back to the theorem. I still need to check that this function is not, that this value is not 0, correct? Let's do it. So it remains to show that this guy, f prime of f inverse of 1, because our a is 0 here, is not 0. That's the last thing I need to check. So I check this, it remains to show that this is not 0. Well, what is f inverse of 1? What is f inverse of 1? What is this guy? Well, let's give it a name. How about we call it b? So if b is f inverse of 1, that's the same thing as we discussed above. That's the same thing as saying that f of b is 1, right? That's the same thing as saying that f of b is 1. Well, look at f of x. It's 2x plus cosine of x. That's the same then as saying that 2b plus cosine of b is equal to 1. Correct? Don't forget, the function is 1 to 1, which means if you find such a b, that's the only b, right? So 1 to 1 again means no image is shared by two distinct inputs, right? So if you find a b so that 2b plus cosine of b is equal to 1, there is no more than one b that does it. That's the only one. Once you find one, that's the only one by the 1 to 1 property, right? Makes sense? So my point is, if you are able to inspect what b can be, if you are able to find that b, then that's the b you're looking for, because the function is not is 1 to 1. That value 1 is not shared by multiple inputs. So that's the guy. If you find a b, that's the only guy that does it. All right. So if you inspect this equation, you should. I mean, if I give you a couple of minutes, maybe you should be able to come up with a b just by inspection. No need to solve here. It's an easy b. So what do you guess? A 0. How about b being 0? 2 times 0 is 0. Cosine of 0 is 1. So it becomes 0 plus 1 is equal to 1. So I'm going to confidently write that that's equivalent to saying that b is equal to 0. And here I'm going to highlight this equivalence by an exclamation mark, just to let you know that something is delicate is going on here. And that delicate part is, if we find, is the following. If we find a b that does this job, that satisfies this equation, that's the only one. This is why you see a double-way street here, an equivalence. That's the only one by the 1 to 1 property, because that output is not shared, because of the 1 to 1 property, is not shared by multiple inputs. So if you find a b, that's the only b. Okay? All right, so b is equal to 0. As such, what's f prime of f inverse of 1? So as such, what can we say? So thus, f prime of f inverse of 1 is equal to f prime of, what is this guy again? What is this guy? That's the b. That's the b, right? And how much was b? Was 0. So that guy is actually 0. That's what we found. Okay? And all this discussion allowed us to transition from here to here. So this is the backbone of, or the, the cornerstone behind the discussion here, right? Okay. And this is equal to what? F prime of 0. F prime of 0. What's f prime of x? What's f prime of x? We found it above, right? What's f prime of something? What was it? It was here. F prime of something is 2 minus sine of the thing. So f prime of something is equal to 2 minus sine of the thing. That's what we found, correct? All right, and so f prime of 0, who's going to take the role of the bullet? It's the 0. So f prime of 0 would be 2 minus sine of 0. So 2 minus sine of 0, and sine of 0 is 0, right? So this is 0. So 2 minus 0 is 2. So it's not 0, right? That guy is not 0. That guy is not 0. Make sense? So as such, by the next theorem, now we can apply not the next, the previous theorem. So by the previous theorem, we can then say that the derivative of the inverse function at 1 is equal to 1 divided by the derivative of the function f at the point f inverse of 1, right? And this is something we just found above. How much was this? F prime of f inverse of 1? We found it to be 2 at the time, right? We found it to be 2. So this means this is a half. Okay. So the tangent line at the curve f inverse, y equals f inverse of x, at the point x equals 1 is equal to 1/2. Okay. All right. Moving on, next concept. Exponential functions and their derivatives. Again, this is something that you've seen before. Let me recall, if you completely forgot about exponential functions, I have a video on this. It's entitled Exponential Functions. Just please revisit that or visit it. And we're going to also talk about their derivatives. So if you recall, the exponential functions had two trends. An increasing trend if the base for exponential functions has to be positive and different than 1. So two options. If the base is bigger than 1, then the trend is like this, the pink one. And has a brown trend, this trend, if that base is positive and smaller than 1. Okay? All right. So then we can have the following two properties. Let's talk about the pink one. What can we say about the limits? As x goes to plus infinity, I'm talking about this. As x goes to plus infinity, the function is going also to plus infinity. So you get that thing. Again, I'm talking about the pink trend, which means I'm assuming the base is bigger than 1, right? So if x goes to plus infinity, the function ax is blowing up. So it goes to plus infinity. And if x goes to minus infinity, if x is going to minus infinity, the function is decreasing all the way to 0, right? Or the function is going to 0. This is 0 plus, correct? 0 plus if you want to be more precise. Okay, and for the brown trend, this means when the base is between 0 and 1, right? When the base is between 0 and 1, what can you say when x goes to plus infinity? When x goes to plus infinity, the function is decreasing to 0. And when x is going to minus infinity, the function is going to plus infinity, right? So you get these. If x is going to plus infinity, I'm talking about this part. If x is going to plus infinity, the function is decreasing to 0. And if x is going to minus infinity, it's going this way, and the function is blowing up this way, right? Plus infinity. All right. Let's evaluate this limit. Limit as x goes to plus infinity of this quotient, e to power 2x divided by e to power 2x plus 1. Well, this is of the form infinity over infinity, correct? Because that part, the top part, blows up, and the bottom also blows up. Do you agree with this? One more time. If x goes to plus infinity, what happens to e to power 2x? Well, if x going to plus infinity, 2x is also going to plus infinity. And e to something going to plus infinity, e is bigger than 1, right? E is bigger than 1. E to something going to plus infinity is plus infinity. Do you agree with that? E to something going to plus infinity is plus infinity. So that guy is going to plus infinity as x goes to plus infinity. Similarly, downstairs, that guy is going to go to plus infinity, plus 1 is also going to plus infinity. So it's of the form infinity over infinity. It's an indeterminate form as previously stated. So we have to do something for, it's indeterminate, so we have to find whether this is defined or not defined. All right, so how can we handle this? Please think about it on your own and then let the video run. So how about we call this guy, actually we don't, let's not call it anything. So the limit as x goes to plus infinity of e to x over e to x plus 1 as we said, this is infinity over infinity, so we have to do some algebraic manipulation here. What we're gonna do is I'm gonna divide upstairs and downstairs by e to power 2x. In other words, I'm simplifying by e to x. So I'm gonna divide upstairs by e to x, and I'm gonna divide downstairs by e to power 2x again. So this is like multiplying by 1, right? Correct? Multiplying upstairs by 1 over e to power 2x and multiplying downstairs by 1 over e to x, this is the same thing as multiplying by 1. So I didn't do anything to the value of that quotient, except I changed the way it's written. Okay, as such, what do we get? So x goes to plus infinity. Upstairs is 1, right? Upstairs is 1. E to power 2x divided by itself is 1. Over here, I mean, this is the same thing as e to power 2x over e to power 2x, which is 1, plus 1 divided by e to power 2x. Do you agree with this? A plus b over c is a over c plus b over c, right? That's what I used here. Okay, and that's equal to what? Where does e to power 2x go to as x goes to plus infinity? It goes to plus infinity, right? We just discussed this. This guy goes to plus infinity. 1 over something that blows up, that's gonna shrink, right? That thing is going to 0 then. So I get that this is equal to 1 over 1 plus 0. One more time. If x is going to plus infinity, twice x is also going to plus infinity. E to power twice x is going to plus infinity, because if the base is bigger than 1, if that guy is going to plus infinity, if the exponent is going to plus infinity, that base to power, that exponential function, a to power that number, is also going to plus infinity. In this case, a is e and x is twice x, right? If x goes to plus infinity, twice x is also going to plus infinity, so e to power twice x is going to plus infinity. So that guy goes to plus infinity. 1 over something that blows up is gonna shrink, is going to 0. That thing goes to 0. So this whole thing becomes 1 over 1 plus 0, which is 1. Does it make sense? All right. I mean, is there anything we can say here? If you take a look at the function e to x divided by e to x plus 1, if you try to graph this, the function is going to have a horizontal asymptote at plus infinity. That horizontal asymptote is 1, right? Okay. All right. Next one, next property. Derivative of the natural exponential function. Natural exponential function when the base is e, right? Euler's number. Well, the derivative, as it happens to be itself. Again, as I mentioned at the beginning of this video, if you would like to discuss any proof pertaining to a result stated here, just let me know. Okay, and I'll record this. I'll record the proof for you. All right. So the derivative of the natural exponential function is itself. I wrote here geometric significance, which means that, any point on EX looks like XEX, correct? If the function here is y equals EX. And what does it mean? That means the geometric significance of this, if you have the tangent line, right? The tangent line, the slope of the tangent line is going to have, according to this, is going to be also EX. So you can say that the slope of a tangent line to the curve y equals EX at any point is equal to the y coordinate, right? It's the y coordinate of the point. Okay. All right, differentiate the function y equals e to power tangent x. So we know how to differentiate e to power x, right? So we know from the previous statement, we know that d over dx of ex is equal to ex. Am I correct? That's what we know. Okay. How about I disguise this. I'm gonna call it something else, star. Okay, I just call it star. Then what we want is we want to differentiate with respect to x that function e tangent x. Correct? And as you see, we don't have the x as we used to do. We don't have that star is not the star, right? The star here and the star here, they're not the same in this case. Over here, the star is x, but that guy is not the star anymore. It's tangent x. Okay? So we don't have this format. If we have this format, then I can apply it. But I don't have this format. However, here I have a function of x, right? I have a function of x. So I hope this brings some memory, right? Chain rule. We're gonna use chain rule. So what I have is I have a function of x here. How about u for the name of that function? Okay, so I have then, I'm differentiating with respect to x a function that's in function of u, which in turn is in function of x, right? So if you call this guy f, if you call this guy capital F, so what you have is that f is a function of u and u is a function of x, right? So you have this chain. And what you want is you would like to differentiate f with respect to x, right? So you would like to differentiate f with respect to x. So the chain rule is gonna, or it tells us that differentiate f with respect to u, and then multiply this result with the derivative of u with respect to x. Correct? Remember this? Written in Leibniz notation? Okay, that's what I'm gonna be needing here. So what I'm gonna have is I'm gonna differentiate this guy with respect to u. So I'm gonna differentiate EU with respect to u, that's the first part, times the derivative of u with respect to x. Do you agree with me? Okay. This is equal to what? For the first part, now I have the structure, that's the star and that's the star. Correct? You see it? It's right there. D over D star is acting at, this operator is acting at E of that star, the same star. Now I have it. So then what can I say? The result is E to that star. And what's the star here? It's U. Make sense? So it's E to power U, again by this result, times the derivative of u with respect to x. How much is u? How much is u? Is tangent. And what's the derivative of tangent? Actually, let me write it. Correct? So let's organize a little bit. All this was needed. All this was needed here. Right, so just go like this. Everything here in this package was needed over here, and this guy, how about we call it this symbol, the yen symbol. Okay, I used it here, and then what? You agree I used it here because I used to rewrite this as EU, right? The star being U. So I used this yen symbol with star being U. Okay, and then this is equal to EU. What's our U again? Tangent. So E tangent of x times the derivative of U, which is tangent, with respect to x. What's the derivative of tangent with respect to to x? What's the derivative of tangent with respect to x? It's sec squared, right? Sec squared of x. Okay, so long story short, the derivative of this function is e tan x times sec squared. Along the way, what did we discover along the way? Along the way, we discovered a result. Let's box it here. So this result is already discovered. It's this part. It's a combination between this formula and the chain rule. So if you have a differentiable function u in terms of x, differentiable, then what we discovered is that if you try to differentiate EU with respect to x, then what we get is u prime times EU, right? It's right there. EU times u prime. This is u prime. So, or equivalently, this is u prime times EU. Okay. So this is like a generalization of this yen formula. Okay. Why? Because it's that it encompasses that, right? When u is the identity function, when u is the function x, so if you replace u by x, u prime becomes 1, and this becomes e to power x, so you get back that formula. But if u is some other function of x that's differentiable, like tangent of x or something else, then you get this improved result. So because of this property, because of this yen property that we call, we can actually say that the primitive of ex is itself, right, plus a constant. So we can have this property then, primitive of ex, dx is equal to ex plus c, where c is an arbitrary constant. And don't forget, I'm gonna keep this this habit of having like a star or something that's representing the variable. I don't want to lose any audience just because of the name of the variable. Okay, think about it as a placeholder. Whatever this guy is, should be this, should be this. All right. Okay, so evaluate the primitive of x squared times e to power x cubed dx. All right. So please stop the video and please think about it. I'm gonna approach it the following way. I'm gonna introduce a new variable. Okay, so I'm gonna introduce a new variable. Let's call it u. So I'm doing U-Substitution to be x cubed. Okay. As such, what can we say about du? Well, du becomes 3x squared dx. Yes? That is to say, 1/3 du is equal to x squared dx. Okay? So then, this integral that we have this integral that we have, let me keep the purple. So thus I can be written as the primitive of, so x squared dx is 1/3 du, right? 1/3 du, correct? And ex cube is e to power u, because x cube is our new notation, or the new variable u is actually this old x cube, right? So that's the transformation I'm doing. So this becomes e to power u, right? Okay. And that's the same, since 1/3 is a multiplicative constant, it goes outside, eu du. So now I see that I have the structure. The star now is u, right? The star now is u. As such, this applies. And what do we get? How about we give it a name? How about we call this leaf? Okay, something like this. So this becomes, because of that property leaf, okay, this becomes equal to 1/3 e to power the star. And who's the star? It's the u, plus an arbitrary constant. And this is then equal to 1/3. So I have to give back the answer in terms of the variable given, which was x. It suffices to just replace u by x cubed, right? This is our auxiliary notation, our auxiliary variable, and that guy is x cubed. So that becomes e to power x cubed plus c, where c is an arbitrary constant. Okay. All right. So if you differentiate that guy, you should pick up x squared ex cubed. Actually do it. Let's do it actually together. Let's differentiate this. Let's differentiate this on the side, just to get used to this, to differentiating the exponential function with base e. So let's differentiate 1/3 ex cubed plus c. If you differentiate that, we get the derivative of each, right? And the derivative of the first is 1/3 times the derivative of ex cubed, correct? And the derivative of a constant is 0, so this becomes plus 0. I'm not going to write it. And then d over dx ex cubed by the yen property, that one, and actually not this one, because I need the chain rule, that one here. So the u is x cubed in our context, so u prime becomes 3x squared. So 3x squared times e to power x cubed, right? This is what this guy is. So 1/3 times 3x squared times ex cubed, and this is x squared times ex cubed, which is the integrand, right? See it? It's right there. Okay. All right, very good. So this is like checking the work. You don't have to do it, obviously, but just to get used to differentiating exponential function with base e, just going back and forth. Next example, find the area under the curve y equals e to power minus 3x from 0 to 1. So when x is 0 and when x is 1. How do we graph this? Certainly this is a positive function, right? This is a positive function. Exponential is never negative. It's a decreasing function. However it looks, doesn't matter how it looks, but all what I know is it makes a dance above the x-axis, right? Because it's a positive function. So whatever it is, maybe something like this, and between 0 and 1. So 0 is this, that's x equals 0, and this is x equals 1. Make sense? And what do they want? They want the area under the curve. So what they want is actually this area here. That's the area. Let's give it a name, calligraphic A. Alright, so we want to find calligraphic A. And what's this area based on our knowledge? That's the integral from 0 to 1, right? Of the function. What's this function again? This is y equals ex e negative 3x. And then we are integrating this function with respect to x, and x varies from 0 to 1, right? X varies from 0 to 1 all the way here. Okay. And this is equal to what? Well, we're gonna use the leaf property, but we cannot use it yet because what we have here, we have e negative 3x squared, right? Dx, not 3, negative 3x dx, right? So if that's the star, I don't see the star here. Make sense? So if the star is negative 3x, I don't see the star here. So I want to do a U-substitution again. And the U-substitution is going to be this negative 3x. The U is going to be negative 3x. So let's do it in order to apply the leaf. So we get I'm gonna do U-substitution. U is gonna be negative 3x, and as such du is gonna be minus 3 dx, right? Okay, that is to say dx is negative 1/3 du. All right, let's see what we get. We get the integral e to power u dx is negative 1/3 du. How about I put the negative 1/3 outside? So negative 1/3 outside du. Okay. And now what are the bounds? What are the bounds? Well, the lower bound goes to the lower bound, as we know. When x is 0, u is gonna be 0, right? So the lower bound of u is gonna be also 0. And when x goes to its upper bound 1, u goes to, so when x goes to 1, u goes to negative 3. Okay. All right. And now if you wanna reverse the bounds, you can just pay the price minus and flip the bounds. So we can get that this is equal to 1/3 negative 3 to 0 eu du, right? And now the leaf applies. Now the leaf property applies. Okay, should have had it green all along anyway. Okay. And get what? 1/3. So what's the primitive of eu du by the leaf? Primitive of e bullet d bullet is e bullet, right? Plus a constant. So we get here e bullet, which is u in this case. This is between 0 and minus 3 and 0. Right? And what is that? That's 1/3 e to power 0 minus e to power minus 3. Which is, what's e to power 0? What's a non-zero base to power 0? That's 1. So that's 1/3 1 minus e to power negative 3. This is certainly a positive entity, right? Because that guy is smaller than 1. Very good. So this is how much this area is. All right, moving on to the next concept, logarithmic functions and their derivatives. If you need a refresher on log functions, I have a couple of videos on logarithmic functions and their properties. So please visit that just in case you want to refresh on it. Otherwise, recall that the log function, the logarithmic functions, are the inverse functions of the exponential functions with the same base, right? So log base a of x is the inverse of the exponential functions with the same base. And since at the time, if you remember, let me take you there, we had two trends, right? The pink and the brown. So the pink trend when the base is bigger than 1, and the inverse function is going to be symmetric with respect to the function, or they're going to be symmetric to each other with respect to the line y equals x, right? So we're going to have also two trends here, a pink one and a brown. Okay, so the pink is symmetric to the pink over there with respect to the line y equals x, and the brown here is symmetric to the previous brown with respect to the line y equals x. Okay, so out of these we can extract two properties for each. When x is going to 0, I'm talking about the base being bigger than 1. When x is approaching 0 from the right, the function is blowing down, and when x is going to plus infinity, the function is blowing up, right? It's the other way than the exponential. It behaves, I mean, since they are symmetric with respect to line y equals x, the y and x are gonna swap, right? So we're gonna have this property, limit as x goes to plus infinity, as the function goes, as the input goes to plus infinity, the output is blowing up, right? And if the input is going to 0 from the right, the function is blowing down. And for the brown one, if x is approaching 0 from the right, if the input is approaching 0 from the right, then the function is blowing up. And if the input is approaching or going to plus infinity, the function is blowing down. It's going to minus infinity, right? So when the base is between 0 and 1, we get these two properties. Okay, so an example: find the limit as t goes to 0 of ln of tangent squared. This is a t, right? This is a t. Okay, fix that. So one more time. Find the limit as t goes to 0 of the function ln of t squared of t. All right, so here's the question. Where does tangent of t squared t go if t goes to 0? Where does this function go as t goes to 0? Remember how you graph tangent of t? Well, that's the graph of tangent of t. I'm going to just graph it around 0 because it's periodic with period pi, if you remember. The graph is around 0, something like this, right? It's an odd function. Tangent, I'm talking about tangent. Tangent, this is a piece of it. That's tangent of t. So tangent square is gonna be symmetric with respect to the y-axis, correct? My point here is tangent of t, where t is near 0, tangent of t is around 0. So tangent square t is gonna be around 0 from the right, though, correct? The y value is tangent of t squared. It's gonna be a function. It's gonna be a function like this, something like this, right? It's gonna be behaving something like this. My point is symmetric with respect to the y-axis, and it's going through 0 because it's an even function now, tangent squared. And then the y value of this function, the output of this function as t is approaching 0, are approaching 0 from above, right? From above. The y values are approaching 0 from above, correct? So tangent squared t is approaching 0 from above, from the right, as t goes to 0. Agree with this? Okay, as such, where does this go? This is going to 0 plus, that's going to 0 plus, and where does ln go when it's input? I'm talking about this being the input of ln, right? That thing. So that thing is going to 0 plus. Where is ln going if that guy is going to 0 plus? Well, first of all, ln is the same as log base e, right? If you remember, ln is log base e. So log base e, the base is bigger than 1. E is, Euler's number is bigger than 1. It's 2.718 or something, right? So it's bigger than 1. So where does log base a of x go when that x go to 0 plus? Well, if x is going to 0 plus, the function is going to minus infinity. Correct? When x is going to 0 from the right, the function is going to plus infinity. So if that guy is approaching 0 from the right, the whole thing is approaching minus infinity. And that's the situation I have. Because this guy is approaching 0 from the right, ln of that guy is gonna be going to minus infinity. Make sense? One more time. This guy here, as t approaches 0, this guy is approaching 0 from the right. So ln of something approaching 0 from the right, as we discussed based on the graph, that thing is blowing down. That's going to minus infinity. Okay. So if you want, you can say this since that, and the fact that the limit as x goes to 0 from the right of ln of x, so I'm talking about x being this guy, right? X being tangent square of t, that's equal to, because tangent squared of t is approaching 0 from the right, so I have this if you call this guy x, so you get that, and this is equal to minus infinity according to what we just said above. Okay, namely this. Very good. Property: derivative of the natural logarithmic function d over dx ln of x is 1 over x for all x positive. Well, for all x positive, I understand why, because ln doesn't operate on negative numbers, right? Or 0. So that's understood. Derivative of this is 1 over x. We're not going to show it, but I'm going to tell you, actually, how would you think we should show this? There are two ways. The natural way is to use the very first theorem that we stated today. Let me take you back there. This. Remember this? So I'm talking about the inverse function here being ln. So the function f is going to be the exponential function. Correct? So f being the exponential function with base e, the natural exponential function. Certainly it's a one-to-one and differentiable. The derivative of ex is ex itself. And its inverse is log base e, right? So what do we get? We get, let me just cram it here. So we get that ln, if you call, so if f of x is ex, that's the same as saying that f inverse of x is ln of, right? So is equal to ln of x. And based on this property, the derivative with respect to x of the function ln of x, right? Let's call x a generic point, is equal to 1 over the derivative of f at the point f inverse of x, right? And what's f inverse of x? ln of x. Okay, and what's the derivative of f again? It's itself, So it's ex. So this becomes 1 over e ln x. Make sense? And what's e to power ln x? Back-to-back exponential function and ln function. Exponential function and logarithmic function with the same base, back-to-back. They undo each other, and you get x because they are inverses, right? So this is 1 over x. So that's 1 over x. So the derivative of ln x is 1 over x. That's what we have, right? So let me take you back there. That's what we have, correct? Let me show you a different way of doing that. Let's do it quickly here. Let's call y to be ln of x. Okay? If you call y to be ln of x, that's the same thing as saying that ey is equal to x, right? If y is f inverse of x, then f of y is equal to x, right? That's what we have. Okay? And then, I mean, this is in some way similar to the previous result. And then what? If you use the implicit differentiation, what can we say? If you use implicit differentiation, what can we say? Let's differentiate this guy with respect to x. Keep in mind that y itself is a function of x, so that's why implicit differentiation is going on here. So the derivative of e to power function of x, and this function we're assuming it's differentiable, okay? By the theorem we know that, the theorem that we just mentioned above. Well, guess what I'm gonna be needing here? I'm gonna be needing this bubble. So the u is gonna be the y. I'm differentiating a function. I'm differentiating with respect to x a function that looks like this: e to power of x, right? That's the y over there, which is ln of x, and it's differentiable based on the theorem. Based on the theorem. What theorem I'm talking about again? This theorem, the beginning of the section. If the function is one-to-one and differentiable, then its inverse is also differentiable. That's why you know that ln is differentiable. Okay. All right, then what do we have? So if you differentiate both sides, you get, what do we get? EU. Differentiate EU, you get u prime, so in this case y prime, times EU, right? Is equal to 1. If you differentiate x with respect to itself, you get 1. Alright, what do I want? I want y prime. I want the derivative of y. So what's y prime? So y prime is equal to 1 over ey, and I can divide by ey because the exponential function is never 0, right? It's never 0. So I can differentiate, divide by this. And this is what? What's e to power y? E to power y is x. So that's 1 over x. So that's this guy. Okay. So the derivative of y, so the derivative of ln is 1 over x. Okay. So this is another way to show it. Again, it uses the theorem because I need the theorem to tell me that something like this is meaningful. I mean, ln is differentiable, and once it's differentiable, I can use implicit differentiation. Okay. All right. Let's see how we can use that. So this is the result. As usual, I'm not gonna tie myself to the name of the variable. I'm gonna call it something else. How about we call the variable again star? Okay. That's the same guy here, here, and here. And I'm using star just not to be so tied to, just the name of the variable. Okay. Differentiate the function y equals ln of the quantity x4 plus pi. Well, I'm differentiating with respect to x. So that guy is x, right? So I'm differentiating with respect to x, the function ln of x4 plus pi. certainly if this is star, certainly what I have here is not the star. As such, I cannot use this property yet. But we know the drill by now, so how about we call this guy U? So I'm using chain rule, right? How about we call this guy U? Okay, let's give it the name U and use chain rule. Use chain rule for this. What do we get? We get that this is equal to the derivative with respect to U, right? ln of U times the derivative of U with respect to x. And now I have this format. I have now the star here and the star here, right? I have the structure. D over D star is at, right? Differentiating with respect to star, the function ln of the star. I have the structure, the star being U now. That's 1 over U. So how much is this? That's 1 over U. That's 1 over U. And here I used which property? So we used property, this property here. How about asterisk? Okay. Times du over dx, so differentiate u with respect to x. So differentiate u with respect to x. And how much is u? It's x4 plus pi. Right? Okay. So it's 1 over u, and u, as we said, is x4 plus pi, times, what's the derivative of x4 plus pi with respect to x? That's 4x cubed. Okay. All right. So that's the derivative of this function with respect to x. Can we actually summarize our findings here as we did previously? So along the way we found the following: if u is a function of x that's differentiable, right, then the derivative with respect to x of ln of u, what did we find it to be? Using the chain rule, we found it to be 1 over u times the derivative of u, right? The derivative of u with respect to x. So it's u prime times 1 over u. And what's u prime times 1 over u? It's u prime over u. So this is what we found. This is the combination of asterisk, this property, the combination of the asterisk with chain rule. Okay. All right. Part 2. Y is equal to square root of ln of x. Okay. So let's differentiate that. Differentiating y with respect to x yields the following. That's derivative with respect to x of the function ln of x to power half, right? And this is what? This is equal to, by the chain rule, if you think about this whole thing as being the function of x, that's the derivative of this guy with respect to ln of x, right? So that's the derivative. How about we call this guy v? Okay, just to see it better. This is then equal to the derivative of x, the derivative of v to power half with respect to x, by the chain rule. We have a property that we developed before. This is the chain rule combined with the power rule, but let's do it again. We get half, all right, we get d over dx v to power half, sorry, not x, I'm using chain rule, so this should be v, right? I'm differentiating with respect to that thing, ln of x. So v times dv over dx. So I'm differentiating this guy with respect to v, and then I'm multiplying by the derivative of v with respect to x. Okay. And then what? And then what? How much is this? How much is this? This is half v to power half minus 1, right? All results times dv over dx. Now I'm differentiating v with respect to x, and how much is v? That's the ln x function, correct? All right, what's that guy? Well, v is ln x, and 1/2 minus 1 is negative half, right? So this becomes ln x to power negative half. Correct? Times the derivative of ln of x with respect to x. Well, you can use either this. If you use it for u to be x, or you can go to asterisk. What's d over dx acting at ln x is 1 over x. So it's 1 over x. Okay. All right, you can write the result as follows. So it's 1 divided by 2x square root of ln x. Okay. What's the domain of this function, by the way? What's the domain of this function? Is it for all positive x? How about I leave it as an exercise for you? What is the domain of this function, square root of ln x? I can assure you that the domain is not 0 to infinity, because there are numbers that allow ln x to be negative, right? Remember ln x, how the graph it looks like? Ln x, it's when the base is e, which is bigger than 1. Take a look. The trend looks like this for ln x when a is e, right? So you see all these guys, all these x allow the function to be negative. And at this number, the function is 0. This is where it starts being a good output to be placed under the umbrella, right? Correct? What is it? Correct? So I need this guy to be non-negative for the square root of this guy to be meaningful. Okay, so the domain, what can you take for x? You want to take for x, you want to choose x to be so that ln of x is bigger than or equal to 0. So based on the picture, it should be what? Complete this. All right, next. I need to differentiate this function, ln of absolute value of x. Okay. Well, what is this function? This is two things, depending on what x is. If x certainly cannot be 0 here, right? Because ln of 0 is not defined. But x can be negative and can be positive, because the bars turns the negative into positive, right? So if the x is positive, then this function is no more than ln x. And if the x is negative, then this is ln of negative x, right? That's what we said. The negative forces that entity to be positive if x is negative, right? Okay, now if you want to differentiate this function, with respect to x, well, you get two pieces. Let me make it bigger for you. We get two pieces because that function ln of absolute value of x is piecewise defined, correct? Well, it's the derivative. You have two pieces when x is positive and when x is negative. When x is positive, what's the derivative of ln of x? So again, I'm differentiating ln of absolute value of x. Ln of absolute value of x is ln of x if x is positive. So under this condition, I'm talking about that. So differentiating this is the same as differentiating that under this condition, right? And what's the derivative of ln of x? What's the derivative of ln of x? What's the derivative of ln of x with respect to x? It is 1 over x, correct? When x is positive. And again, this x I should have labeled it as the star, right? Okay. All right, back to here. So that the derivative of this is 1 over x. When x is positive. And down here, the derivative of this function, now that function is this piece. So differentiating that is the same as differentiating with respect to x, that guy, ln of negative x, right? And how do you differentiate that? We have a result. You see this result? Who's u now? U is negative x. U is negative x. I'm differentiating with respect to x, ln of a function of x, which is u, which is negative x in this case. So it's u prime divided by u, right? So it's u prime divided by u. That's my u. Let me highlight it for you. That's my u. So it's u prime over u, right? Based on that bubble that we just referred to. Okay. And what's u prime over u? What's u prime? What's the derivative of this with respect to x? Negative 1. And what's u? U is also negative x. So how much is this? That's 1 over x again. 1 over x again. If x is negative now. Make sense? So what can we say? We can summarize that result that we just had. The derivative of ln of x is 1 over x, regardless what x is. I'm going to record it in the next property, but allow me to write it again here. Ln of absolute value of x is equal to 1 over x, irrespectively of x, as long as it's not 0, right? Makes sense? So because no matter what x is, whether it's positive or negative, 0 is not part of the game, the derivative is 1 over x, as we found. So this is the property I was talking about. Okay. All right, and since we know that the derivative of ln of absolute value of x is 1 over x, now if you integrate this, you should get back that plus a constant, right? So we have the corresponding integration formula, which is this. If you integrate this with respect to x, you get ln of absolute value of x plus c. Make sense? Obviously, x cannot be 0. Okay. Determine the area of the region under the hyperbola xy equals 1 from x equals 1 to x equals 2. So how do you graph this function, this hyperbola, a piece of it, just from 1 to 2? Well, this is the same function as y equals 1 over x, right? This is y equals 1 over x, as long as x is not 0. Right? As long as x is not 0. Well, x cannot be 0 to begin with, because if x is 0, 0 times a number cannot be 1, right? So x certainly not 0. Okay. And how do we graph that? Between 1 and 2? Certainly because x is positive, between 1 and 2, right? X is positive, so this is above the ground, and maybe something like this. Okay. This is between 1 and 2. X equals 1 and x equals 2. And what's that area that they're talking about? That's the area. That's the area they're talking about. So how about A for area? And what's this green function? What's this green function? This green function is y equals 1 over x. Correct? So what's the area then? Let's compute it. That's the question. They need the area. So let's compute that. So the area is the integral of the function 1 over x dx, because the function is positive, so the net area becomes the area itself, right? And the x varies from 1 to 2, correct? Remember this property? Okay. All right. And what's the primitive of 1 over x dx? What's the primitive of 1 over x dx? It's ln of absolute value of x plus a constant. We're not going to worry about the constant because this is a definite integral, right? So that's ln of absolute value of x between 1 and 2. Okay. No need for the bars here. We don't need the bars. Why? Because x is positive. Between 1 and 2, x is positive, right? Between 1 and 2, x is positive. Okay. So that's ln of 2 minus ln of 1 then. Ln of 2 minus ln of 1, right? Ln of 2 minus ln of 1. And what's that? Ln of 1 is 0, right? This is where the function ln crosses the x-axis. This is where the function ln, where the base is e, crosses the x-axis, right? When at 1, the value of the function is 0. So ln of 1 is 0. And this whole thing then reduces to simply, so this whole thing reduces to ln of 2. And ln of 2 is positive, right? ln of 2 is positive. Why? Let me again refer to the graph. 2 comes after 1, so 2 is somewhere here. And ln of 2, the base is bigger than 1. We still have the strand, the pink one. So if 2 is somewhere after 1, so somewhere here, ln of 2 is certainly the y value. If the input is 2, the y value, which is ln of 2, is positive, right? Okay. Very good. So back to this. So we're done with that. So it turns out that the area here is ln of 2, wherever this number is. Okay. Example. Calculate the primitive of tangent x dx. Okay, so calculate this. Let me, since I have more room here, just take it. All right. So how can we integrate this guy? Well, how about thinking about, certainly before you actually try to listen to me, don't even try before you think, because you're not learning anything. So please stop it and think about this on your own. I'm gonna look at tangent of x as sine of x over cosine of x. Okay, so I'm gonna look at this as sine of x over cosine of x. This identity, we know it from trig, right? Dx. Okay. And this is equal to, I'm gonna do a substitution. How about we call u to be cosine of x, and as such du is negative sine of x dx. Agree? So that is to say, sine x dx is negative du. Correct? So we get this. All right. Therefore, this integral, the pink one, is equal to the integral of, we called cosine u, right? We called cosine u. So downstairs I have u. And what's sine x dx? What's sine x dx is negative du. So I get that. Yes? One more time. Cosine x is what we called u. As such, sine x dx is negative du. Okay, and this is the negative, or the opposite of the integral, du over u. And d over u is the same as saying 1 over u, right? du. So that's the same as this. Okay. And now, if you go back to this result, this one, again, ignore the name of the variable. How about star again? So every time I see x, I'm putting it, I'm hiding it. So this becomes primitive of 1 over bullet d bullet. That's equal to ln of the absolute value of the bullet plus a constant, right? Do we have that? Do we have primitive of 1 over bullet d bullet? Yes. The bullet is the u then. All right, let's give this guy a name. How about double asterisk for a name? So here I'm gonna use double asterisks. And we get that this is equal to minus ln of the absolute value of u plus constant. Okay. Excellent. And what's u? U is cosine of x, right? So cosine of x plus a constant. All right. I mean, you can stop here, but let's keep going. Let's try to write this in a slightly different way. Look, do you see this? I mean, this is a full answer, no doubt. But let's keep going just to approach it. I don't know which one is in the book, but just in case you use many books, they refer to the primitive of tangent. Depends on the book that you're using. So let me give you all the versions I know. You see this minus? I'm gonna push it because of one of the properties of log. Coefficients, multiplicative constants here, coefficients can be pulled all the way to the exponent level, right? So that's the same by one of the properties of logs. So namely log base a of a to power c is equal to, okay, let's use a different c because I have a c here. About alpha is equal to alpha log base a of a, right? That's the property I'm alluding to. I'm using it backwards now when alpha is -1, right? This is -1 times, so alpha is -1 and the base little a is e and capital A is this absolute value of cosine, correct? So that's what I'm using. I'm using this with alpha being -1, little a to be e, the base, and capital A to be the absolute value of cosine. Okay. As such, I can push that alpha all the way to the exponent level and get what? And get ln of absolute value of cosine of x to power -1 plus a constant. Right? And what's something to power -1? What's a number to power -1? It's the reciprocal of the thing, right? It's the reciprocal of the thing. So that becomes ln of 1 over the absolute value of cosine of x plus a constant. And 1 over the absolute value is the absolute value of 1 over that guy, right? So I get that. Because absolute value of a quotient is the quotient of the absolute value, and since absolute value of 1 is 1, I get that, right? Okay, and what's 1 over cosine? What's the notation of 1 over cosine? That's the function secant. So that's ln of absolute value of secant of x plus c. Okay, so some people use that. Obviously c is a real number here, so where c is a real number and arbitrarily chosen. So some people use this as the primitive of tangent, some people use that. They're the same, so just use your, decide which one is your favorite and go with it. Okay. Let's move on now to, let's recall the change of base formula. So change of base formula says the following. If a and b are two positive numbers, each one of them is different than 1, then log base a of x is equal to log base b of x divided by log base b of a. And this is for any number x that's positive. Okay, again, if you need the proof of this, it's in one of the videos, particularly the videos that has the properties of logs in it. Alright, so I'm gonna use it. I'm gonna specialize the b to be, I'm allowed to specialize b to be any positive number different than 1. The way I'm gonna choose it, I'm gonna choose it to be e, Euler's number, approximately 2.718, right? As such, this becomes ln of x upstairs, and downstairs becomes ln of a, right? And if you differentiate this, if you differentiate this guy, what do we get? So if you differentiate this guy with respect to x, you're gonna differentiate this guy with respect to x, correct? And this is for any x positive. But ln of a is a pure constant. A is a constant, right? It's not the variable. A is a constant. So you can push that 1 over ln of a outside. And then times derivative with respect to x of ln x. And how much is this? What's the derivative of ln x with respect to x? That's 1 over x, right? So this becomes 1 over ln a times 1 over x, which is 1 over x times ln a. And this is for any x that's positive. Make sense? So we get this result. It's right there. This is what we just showed. All right. I have another result here. So for positive numbers a different than 1, the derivative with respect to x of a to power x, that exponential function with base a now, is equal to a to power x ln a. And as such, the corresponding integration is primitive of that, or primitive of ax is going to be, if you divide by 1 over, if you multiply by 1 over ln of a, you get that this is going to be the primitive function, right? Makes sense? If you divide here both sides by ln of a, you get that result. Why this is true though? So I know why this is true. This is true because that's true. One more time. Why this is true? Because if you divide by ln a both sides, that's going to disappear here, and the ln a is going to show up here, 1 over ln a. But this would be a multiplicative constant. You can bring it inside. This becomes a to power x divided by ln a. So which means primitive function of ax is ax over ln a plus a constant. Okay, so I know why this is true as long as I show this. But why this is true? Well, let's see. So if you call y to be ax, that's the same thing as saying that, right? I'm calling this guy to be ax, and I would like to find the derivative of this guy. That's the same thing as saying that log base a of y is equal to x. Agree with that? Because the exponential function with base a and log base a are inverses of each other. So a to power x equals y is the same thing as log base a of y is equal to x. Okay. And now if you differentiate, keep in mind this result, right? If you differentiate both sides with respect to x, using implicit differentiation, what do we get? If you use implicit differentiation, you're differentiating this with respect to x. Y is a function of x, so I'm gonna use that. I'm gonna get, using chain rule, I'm gonna get what? I'm gonna get y1 over, using chain rule, right? So I'm gonna differentiate this guy with respect to y first. So I'm gonna get 1 over y ln a times the derivative of y with respect to x, right? Y prime is equal to 1. And y prime is the thing I want, right? Y prime is the thing I want. I want the derivative of ax, which is the derivative of y. That's the y, right? Okay. This means y prime is equal to y times ln a, right? Y times ln a. And what's y? What is y? That's ax. Okay. So that result allows us to find that the derivative of y, which is ax, so the derivative of ax is actually ax ln a. Ax ln a. This is why this result holds. It holds because of that. Okay. All right. So this is like a little proof here for that discussion. Now differentiate y equals 10 to power x cubed. Okay, so please contrast this with this and try to do it. Differentiate y equals 10 to power x cubed. Again, the name of the variable doesn't matter, right? Because it's a dummy letter. I'm gonna go back to my start thing and let's use it. Differentiate with respect to x, that guy, 10 x cubed. If apparently x is the star here, that's not the star. That's not the star. This is a function of the star, right? This is a function of the star. So chain rule, let's call it u. This is a composition of two functions. So I'm gonna differentiate with respect to u. So chain rule, right? Chain rule. So I'm differentiating 10 to power u with respect to u. I'm multiplying this with the derivative of u with respect to x. Okay. Now I have this format. Look, that's the star. That's the same star. Right? So that means that the derivative of this is going to be, who's the a? The a is 10. So that's going to be 10 to power that star ln of a. Okay? So the star is u, so that's going to be equal to 10 to power u times ln of 10. That's for the first part. Okay? So this guy is equal to this whole box times the derivative of u with respect to x. The derivative of u with respect to x, and u is x cubed. So times the derivative of x cubed with respect to x. Okay. Well, what's that then? This is 10 to power x cubed times ln of 10, I'm just replacing what u means, times the derivative of x cubed with respect to x, that's 3x squared. Okay. And if you want to follow the folklore, people typically write it as 3 ln, maybe the ln of 10 is at the end. So 3 x squared 10 to power x cubed ln of 10. Okay. Alright, so the last, I'll just shuffle them around because multiplication is commutative. Nothing crazy here. Alright, so the derivative of this function happens to be this guy. Next, evaluate. Since I have room, how about taking it all the way to the top? Okay, so let's evaluate this definite integral from 0 to 5 2 to the power x dx. Do I know how to integrate such a thing? Yeah, it looks like that, right? This looks like primitive of 2x dx. So a is 2 then. A is 2, right? Primitive of ax dx. And what is it? It's 2 to the power x over ln of 2 in this case. So that's 2 to the power x over ln of 2. And this is between 0 and 5. How about we give this guy a name so we know what we used? How about we call this guy something? How about lambda? Okay, and let's call also this guy, since we used it, also something. How about xi? Okay, so I used xi here at the time. Correct, I used it here. And then I'm using the other one, which is lambda, I think we called it, over here. And then this is, I'm replacing now x by 5 and subtracting the evaluation with that guy being evaluated at 0. So at 5, this is 2 to the power 5 over ln of 2 minus 2 to the power 0 over ln of 2. Alright, 2 to the power 0 is 1, and 2 to the power 5 is what, 32? So 32 minus 1 over ln of 2, because it's the same denominator, I can just put them under this common denominator, and this is 31 over ln of 2. Okay. Alright, let's see this comment here. The calculation of derivatives of complicated functions involving products, quotients, and powers can often be simplified by taking logarithms. The method used in the following example is called logarithmic differentiation. So what I'm going to use here, I'm going to write the formulas that I'm going to be needing. So if you recall the properties of logarithms, we know that if a is positive and different than 1, and if capital A, capital B, and capital C, just B, A and B, are positive numbers, are positive, and C is an arbitrary real number, then we know the following: log base A of A times B is equal to log base A of A plus log base A of B, right? So the proof of, the proof of all three of them can be found in that video that I alluded to. It's labeled as properties of logarithms. If you don't care about the proof, don't worry about it. So plus here. And also log of a quotient is equal to log base A as the difference of the logs, right? So we have that. And the last one, the one that I just mentioned above, log base A of A to the power C is C times log base A of capital A. Okay, so these are the properties that I'm gonna be needing here. I'm gonna call them 1, 2, 3, and this is part of the recall, right? Okay. All right, let's do 1. Differentiate this complicated looking function, and here you see that you have powers, you have product, and you have quotients, right? You have powers here, so it looks complicated, but that tool that I'm about to to illustrate the logarithmic differentiation is going to simplify that thing. Because look, if you want to go, I mean, typically before the one I'm going to introduce, typically you go for quotient rule, right? And you see, I mean, you kind of sense that it's going to be a little long or complicated. So how can we pursue here? One. So the y is x to power 3 over 4 square root of x2 plus 1 divided by this quantity to power 5. Okay. So let's apply log to both sides, and let's apply log base e. Okay. Let's apply the natural log. If you apply the natural log, you get that ln of y is equal to ln of this quotient, right? Over 3x plus 2 to power 5. Okay? And log of a quotient, property 2, log of a quotient is the difference of the logs. So that's then equivalent to ln of y equals ln of x 3 over 4 times the square root of x2 plus 1 minus ln of, I don't like this, so ln of 3x plus 2 to power 5. Okay, and this is by property 2. Log of a quotient is the difference of the logs. Alright, then I'm going to use property 1. This looks like ln of a product. Property 1. Ln log of a product is the sum of the logs. So I get, by property 1 now, I can write ln of y equals ln of x to power 3 over 4 plus ln of square root. You agree that square root is power half? So power half minus ln of 3x plus 2 to power 5. Okay? Alright, next I'm gonna appeal to property 3. That allows me to push that power, that exponent down to the coefficient stage, to the coefficient level. Becomes a multiplicative constant. So each power here, the 3 over 4, I'm going to push it down. I'm going to push the 1/2 down, the 5 down, right? So I get property 3 now. Ln of y is equal to 3 over 4 ln of x plus 1/2 ln of x squared plus 1 minus 5 times ln of 3x plus 2. Okay? Alright, now look at this function. Let's differentiate using implicit differentiation here, because y is a function of x, right? This is what y is. It's a function of x, obviously. So we're going to use implicit differentiation. So we use implicit differentiation and get what? I'm going to differentiate both sides with respect to x, right? Let's differentiate this side with respect to x. What's the derivative of ln of y? What's derivative? How about we call it? I forgot what we labeled it at the time. So derivative with respect to x of a function u, which is a differentiable function. What we get at the time was u prime over u, if you recall this part, right? So we know this one. To be honest, I forgot what we call it. I don't know if it had a name. Let me see. Where is it? was which one was it? Let's see. Oh, it was this one, right? Okay, it didn't have a name, so forget about it. Okay, let's just keep it like this. So I'm using implicit differentiation both sides. That's gonna be y prime over u. So y prime over u, y prime over y, sorry. Y prime over y. Recall, what do we want? We want y prime. We want to differentiate y, right? That's the question. So we want y prime. Okay, it's part of the game now. It's part of the game. Equals, and then I'm differentiating this right hand side. Okay, so we're gonna differentiate because it's sum and differences. So the derivative operator is, the differential operator is actually linear, so it splits sums and allows multiplicative constants to go outside. So this becomes 3 over 4 derivative of ln x over dx, so derivative with respect to x, plus 1/2 derivative of ln of x2 plus 1 with respect to x, minus 5 the derivative of ln of 3x plus 2 with respect to x. Okay, and you know what, since we haven't differentiated on the left side, I'm gonna keep that thing on the right side. Since we haven't differentiated on the right side, I'm gonna keep it the same on the left side. So d over dx ln y, right? But we've done that. This is y prime over y because of this. So this implies y prime over y. Equivalent, they're the same. How about this guy? 3 over 4 times, what's the derivative with respect to x of the function ln x? Well, this is when u is x, so u prime is 1 and u is x, so 1 over x plus 1/2 times the derivative now of ln of x squared plus 1. Sorry, okay, copied it wrong. So I meant it to be ln of u, and in my mind I was seeing it ln of u. Now I saw it to be u. So this is ln of u, right? Okay, let me erase it and write it nicely. So this is derivative of ln of u with respect to x. Okay, that's what I meant. Okay, so then what? So 1/2 the derivative of ln of x squared plus 1, that's the u, so we get u prime. Remember what the u is? U is x squared plus 1 in my context. U is x squared plus 1. So u prime over u becomes 2x over x squared plus 1, because the derivative of x squared plus 1 is 2x. So 2x divided by x squared plus 1. Makes sense? I repeat one more time. Over here I use the u to be x. That's the u. Over here I used this guy to be u. So I get u prime over u by this property. Minus 5, who's the u now? That's the u. So minus 5 times u prime over u, and u prime here is 3, right? So 3 over 3x plus 2. Okay? So we use this property 3 times over here. Let me take it for you, place it here. Okay, place it here, make it smaller. Okay. Actually, this u is part of the other one. And then, so I use this guy 3 times. How about 2 power 3? Okay, so that's Very good. Okay, and then what? Sure, we can do some aesthetics here. The 2 and the 2 cancel. But the bottom line is we want y prime. So y prime, so out of this I can say y prime is equal to y times, 3 over 4x plus 2 and 2 cancel, so x over x squared plus 1 minus, how much is this? 5 times 3 is 15 divided by 3x plus 2, right? Looks good. Okay, so again, what's y? Y is this whole thing, right? That's what y is. Okay. So this is equivalent to y is equal to x to power 3 over 4 square root of x squared plus 1. That's the y guy, right? That's the y guy. 3x plus 2 to power 5 times 3 over 4x plus x over x2 plus 1 minus 15 over 3x plus 2. Okay, so this is what, okay, y prime, I forgot to write y prime. So this is what y prime is. I copied the y back to what it means and that guy, right? So certainly this is, I mean, I took all the steps here, but certainly if you do it, you can actually jump from here immediately to the last part by combining these steps if you're more accustomed to this, to these type of computations. But the bottom line is, look, if you were to do it using quotient rule, this is very, 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 I mean, complicated. It's complicated based on calculation. It's not complicated because it's hard. It's just a lot of tedious computations. So this technique, the logarithmic differentiation, is very helpful. So what are the steps here for logarithmic differentiation? We took log of the function and then we differentiated it using implicit differentiation, correct? All right. So the next one, what's the next one? I want to differentiate y equals x to power square root of x. So we want to differentiate y equals x to power square root of x. Okay. Let's do it in two different approaches. So let's use the first approach as above. So first approach using logarithmic differentiation, right? Logarithmic differentiation. So I'm gonna apply log base e both sides. So ln of y is equal to ln of x square root of x, and by property 3 here, what do we get? We get that this is ln of y equals to square root of x ln of x, right? Look here, I'm not talking about where this function is defined, okay, even though we can, but we're not talking about where it's defined. We're saying what we're doing is whenever y prime is defined, we need to find. Whenever the function y prime is defined, we need to find it, okay? So for example, here the function is not defined when x is less than 0, okay? Even when x is 0, this function is not defined. And I did the same thing here. I should have talked maybe more about it. Over here, this function y, I mean, look, we divided by y and then we multiplied by y, right? If y is 0, this is nonsense. I mean, I cannot divide by 0, correct? And y is probably 0, because if x is 0, this is 0. correct? The domain of y is 0 to infinity, including 0, right? Because look, this is fourth root of x to power 3, so x should be bigger than or equal to 0 for this to be defined. This is defined everywhere, and this guy is defined everywhere, and the only guy that makes the denominator 0 is a negative number, negative 2 over 3, which is outside of the domain for this entity to exist. So the domain here is 0 to infinity. But what we found, right, look, I talked about ln of x, and x being 0 is part of the domain, correct? Part of the domain, as we just said. And this is nonsense if x is 0. Since x being 0 is part of the domain, this is nonsense. So what I'm saying is, what we found here is the derivative of y, of the function y, as long as x is not 0. And for all x bigger than 0, to be more precise. Okay? So this is true if you want to write this. This is true for any x bigger than 0. Let me write it for you. You don't have to be that specific. Well, I'm just telling you that I'm kind of like focusing more on the computation rather than the theoretical aspect. But that's the theoretical aspect behind it. So this is true for any x bigger than 0. Okay? I can't talk about 0 because look, all along, I mean, from the get-go here, this is nonsense, right? This is nonsense, because if x is 0, I cannot say ln of 0. This is nonsense. So what we did is, we found y prime for any number x in the domain, but not 0. And the domain is 0 to infinity, right? Okay, so don't worry about this part. I'm just giving you some or more precise details about that. Over here, same thing. I'm gonna apply without talking about the domain of the function. I'm gonna just say whenever it exists, let's do it. You may ask, what's y prime at 0? What's the derivative of y of this function when x is 0? Well, that's a different issue. Okay, that's a different issue. As a matter of fact, y prime is not defined at 0. So you go to the definition and you try to do it. Definition of derivative, you try to do it, you're going to find infinity. You're not going to find the limit is not going to exist at 0. Okay. Anyway, so don't worry about this discussion. Just if you care about the theory, I'm just giving you some more insights. Very good. So back to this. So what do we want? We want y prime, right? All right, we're using implicit logarithmic differentiation. So then, if you use implicit differentiation here, so implicit differentiation yields what? The derivative of ln of y with respect to x is equal to the derivative with respect to x of this function, square root of x ln x, right? This is a product here. So that means y prime, we did this before, right? This is y prime over y. We did it here, or is it? Over there, right? From this step, because of this property, y prime over y is equal to, let's use product rule. Let's use product rule here. So the derivative with respect to x of square root of x times ln of x plus square root of x times the derivative of ln of x, right? Okay, which means what? Again, this is equivalent, which means what? Y prime over y is equal to, what's the derivative of square root of x with respect to x? It's 1 over 2 square root of x times ln of x plus square root of x times this guy. And what's this guy? This 1 over x. All right. Now what's square root of x over x? What's square root of x over x? That's the same as 1 over square root of x, right? Correct. I'm doing this step just for aesthetic reasons, just to put it under the same denominator. You don't have to, but let's do it. So that's the same as y prime is equal to y. I'm multiplying by y now, right? Both sides by y. Y is not 0 because x is not 0, right? X cannot be 0. So you get y times the quantity 1 over 2 square root of x ln x plus 1 over square root of x. Okay. And if you put them under the same, okay, y is what? Y is x square root of x. So y prime is y, which is x square root of x, times, let's put them under the same denominator, which is 2 square root of x. So upstairs I should have it 2. So ln of x plus 2 upstairs, divide by 2 square root of x. Agree with me? This is what y prime is. This is what the derivative of this function is. This is the first approach. The second approach is the following. Recall that if you have a to power b for appropriate choices of a and b, right? Certainly a is positive and different than 1. So for a positive and different than 1, a to power b is the same as e to power b ln of a. Do you agree with that? Why? Because, I mean, look, this guy here is e ln of a to power b. Do you agree with that? If you use property 3 stated above, you take this b, just talk about the exponent part. You can take the b and put it on as an exponent for a, right? You get this. And now exponential, they're the same. So exponential base e, logarithmic base e back to back, they are inverse functions, right? So they undo each other and you get back that. So you get back that part. This is just that a to power b, right? So back to back exponential with the same and logarithmic functions with the same base back to back, they undo each other. The base here is e, so you only get that survivor here, right? All right, so this is why this is true. Okay, and I'm gonna use it. How I'm gonna use it? Well, our function here is x to power square root of x, right? And we said that x cannot be well, x for sure cannot be negative, because if x is negative, square root doesn't make sense. And x cannot be 0, because if x is 0, this expression becomes 0 to power 0, and 0 to power 0 is one of the indeterminate form, and an indeterminate form cannot be assigned a single number, a single value. So this is only defined when x is positive. Okay, so I'm gonna think about a being x and b being square root of x, and certainly the base is positive. It can be 1. Actually, I don't need this condition here, right? This condition is not needed here. I thought I'm gonna take it as a base. I took the base to be e. So if a is 1, this is meaningful. So a is allowed to be 1 here, no problem. All right, so then what do we have? So I'm gonna take the base to be a, which is x, and we just discussed that guy is positive, and that exponent is the guy b. Okay, so what do we get based on this? What do we get based on this? Let me highlight that. So I'm using this here with, again, that's the a, the base is a, and the exponent is the b, right? And the base in our context is positive, as we just said, cannot be 0 or less. Okay, then I can rewrite this expression as e to power b, which is square root of x, times ln of x. Agree? Can use it like this. Okay, and then what? Now we differentiate y with respect to x, and we use one of our properties that we most likely we called it something. I'm not gonna go back to it. I'm referring to this derivative with respect to x of this function. Here u is a function of x that's differentiable. So the derivative of this, we found it to be u prime eu, right? That's what we found it to be. I'm gonna use it. Okay, so we get what? Who's u here? That whole thing is u, right? That whole thing is u, the exponent part. So we get u prime. So the derivative of that guy, square root of x ln x, times eu, right? Eu, and u is again this guy. Make sense? Okay. And what's the derivative of this? We've done that. It's right there. Where is it? It's right there. We've done this. And if you remember, whatever that guy was, it was all of this at the time. We multiplied it by y at the end of the day. And y meant to us the function x square root of x. Correct? So that's the same thing. If you differentiate that, you're going to get exactly as we did above, and times this. And what is this? Well, that's the function again. So we're going to get the same answer again. So how about putting here dot dot dot, and by dot 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 I mean just go back, see work above, right? So see the work above. Which work I mean? I mean the derivative of this product. We've done it above. We used product rule and so on. I'm not gonna redo it. And then this is equal to that guy, which was at the time, at the end of the day, it was this, right? ln of x plus 2 divided by 2 square root of x times this piece. But this piece is y. This piece is y, which is x square root of x. Correct? So this piece is x square root of x. And we get back exactly as we found before. So ln of x plus 2 divided by 2 square root of x times x to power square root of x, as we just found before. Alright, I just wanted to introduce this just because it brings that angle, which is not seen here in some sense. Okay. Alright. Next example. Evaluate this limit and deduce this limit. Okay. Part 1. We're gonna evaluate the limit as x goes to 0, 1 plus x to power 1 over x. Okay. The way I'm gonna do it, I'm gonna think about this property. Again. Okay. So this property, let's write it. So if the base is positive, we know that a to power b is equal to e to power b ln of a. Right? Who's the a, who's the b here? Clearly the a is the base, so 1 plus x, and certainly as x approaches 0 from any side, x being so small, that entity is positive, right? That entity is positive. 2 power 1 over x. So this becomes limit as x goes to 0, e, right? E to power b, b being the 1 over x, ln of 1 plus x. Okay, now I'm gonna use continuity of the function exponential base e at the point 0. So exponential is continuous at the point 0, so I can, so the exponential function is continuous. It's continuous everywhere, but in particular at 0. So I can say that the limit, right? So not only this, but this is the primary ingredient. I'm also using the fact that composition of continuous function is continuous. So we can bring that limit inside to get this, right? Okay, and what is that guy? So that's equal to e limit as x goes to 0 ln of 1 plus x divided by x. Okay, agree with this? And let me just say one word and then I'll explain. Let me write it and then I'll explain it. Minus ln of 1 plus 0. Okay, so what is that? What is that? Look, let me take you back to the definition of, if you have a function g, what's g prime at a? Isn't it the limit? This is the definition here, right? That's definition here. Isn't it the limit as x goes to a, g of x minus g of a divided by x minus a, right? So how about taking g of x to be ln of 1 plus x and a being 0. Okay, one more time. So this is definition, we know that. Now, how about we talk about, or we rewrite this definition when g of x is ln of 1 plus x and a being 0. How can you write this definition then? We know that this function is differentiable, right? We know this function is differentiable at 0. I mean, we talked about this above. We know exactly where this is differentiable. This function is differentiable for any x bigger than -1, right? As long as this guy is bigger than 0, remember? And this guy is bigger than 0 if x is bigger than -1. Anyway, so my point is that 0, this function is differentiable. As such, this is gonna be a finite thing, and the derivative of that guy is gonna be that number. Okay, how would you read this equality for such choices? Forget about the left side for a second. This right side becomes the limit as x goes to 0. Compare it here. Limit as x goes to 0. G of x, what's g of x? ln of 1 plus x. You see this? Minus g of a. What's g of a? G of a is ln of, g of a is a0, is ln of 1 plus 0, correct? ln of 1 plus 0 divided by x minus 0. What's x minus 0? X minus 0 is x. Okay, all right, why did I introduce this guy without paying any price? What's this guy? This is, at the end of the day, ln of 1, right? And ln of 1 is 0, so that guy is 0. I can write it. This is 0. But why it's useful to write it? Because now you can see that we're talking about this whole thing then is actually the derivative of this function at the point 0. Make sense? So I'm using that. Oops, just a second. Let me go. So I'm using that with these choices, right? So we agreed that this exponent now can be seen as, so the exponent now can be, I'm sorry, not this equality. Actually, it goes here. So we agreed that this is equal to e, right? And this whole exponent now, this whole exponent is the derivative of the function, is the derivative of the function, this function, ln of 1 plus x at the point 0. So it's the derivative with respect to x of this function, right, at the point x equals 0. Agree with me? Now what is that? What's the derivative of ln of 1 plus x at the point 0? So what's the derivative of with respect to x of ln of 1 plus x? Well, what's the derivative of ln of u with respect to x? It was u prime over u, right? So it's 1 plus x prime, the derivative of that guy, divided by u, which is 1 plus x. Now what's this? Upstairs, the derivative of 1 plus x is simply 1 over 1 plus x, right? So one more time, what did I use here in this equality? I used the derivative of ln of u, right? I used the derivative of ln of u with respect to x is u prime over u. That's what I used. And then I transitioned. As such, this becomes u prime over u, and the derivative of 1 plus x is 1 divided by 1 plus x, right? So now I want to evaluate at 0. So if you evaluate this guy at 0, when x is 0, what do we get? 1 over 1 plus 0, right? I'm evaluating at 0, so we get 1 over 1 plus 0. And how much is this? That's 1. Okay. So this package is what I need actually to say that this whole exponent is 1. This whole exponent is 1, and what's that result then? This is e to the power 1, which is e. Make sense? All right. So now we know how much is this limit. This limit is actually e, Euler's number. Now for the second part, we need to deduce the limit as n goes to plus infinity of this quantity 1 plus 1 over n, and I'm missing an n. All right, I'm missing an n. Let me just fix it. So we need to deduce. We need to, based on this part, we need to find that number. Okay, that limit. Okay. All right. So let me just cram it here in this corner. So we have, so this is part 2, right? We want to find the limit as n goes to plus infinity of the quantity 1 plus 1 over n to power n. Okay? So what I'm going to do is, I'm going to use a substitution. I'm going to replace 1 over n by x. I'm going to introduce a new letter, x. As such, what we get? This becomes the limit of, so every time I see 1 over n, I'm going to write x. So this becomes 1 plus x. 1 plus x And what is that power? If x is 1 over n, what's n? I'm talking about that power. If x is 1 over n, what's n? Isn't it 1 over x? Solve for n here. If x is 1 over n, doesn't mean that n is 1 over x. So n is 1 over x. I can rewrite this n as 1 over x. So 1 over x. And now if n goes to infinity, x goes where? If n goes to infinity, if n goes to infinity plus infinity, so this guy downstairs is blowing up, where does the quotient 1 over n, which is x, where does this go? This is going to 0, right? That's going to 0. It's going to 0 from the right, actually. Correct? So it's going to 0 from the right. Why from the right? Because, I mean, certainly it's going to 0. Why from the right? Because n is going to plus infinity. That number is always positive, right? It's decreasing while being positive, though. So that's why decreasing to 0. This is what this means. Okay. Very good. So, and now does this resemble anything that we've worked with? Yeah, it's part 1. This is a two-sided limit. I just need it. I mean, a two-sided limit exists if and only if the two one-sided limit both exist and they are equal, right? I'm talking about the right hand limit now with a plus, and since the two-sided exists, that one-sided is going to be equal to that two-sided. And how much is this? This was e, right? This was e. So this is simply e by part 1. That's the deduced part, right? That's the deduced part. So part by part 1, I deduced that this is e. Okay, so this is short. All right, so we have two writings of e now, in addition to what we know. Both of these are actually e. Excellent. Next, the next topic is inverse trig functions and their derivatives. So the first question is, what's the derivative of the function arcsine of x? Again, if you forget trig functions, inverse trig functions, I have a video on this too, so please visit that video to refresh on that. Now, so sine inverse is a function that goes from where to where? What's the domain of the inverse function, of the arcsine function? It goes from negative 1, 1, right? Negative 1, 1, all the way to negative pi over 2, pi over 2. Okay, remember this? Okay. And we want to find the derivative of this. So we want to find the derivative of y, which is the derivative of sine inverse of x. Well, number one, we know that sine is a differentiable function, right? And if you restrict it on minus pi over 2, pi over 2, it becomes a one-to-one function. If you go now back to the very first theorem in this section, that one, right? If you go back to this, your function sine is 1 to 1. It's a restricted version of the entire sine. It's just on minus pi over 2, pi over 2, right? The function on minus pi over 2, pi over 2, the sine function is 1 to 1, and it has an inverse, arcsine. Okay, it's differentiable. It's differentiable everywhere, let alone on minus pi over 2, pi over 2. And as such, the inverse function, arcsine, is going to be differentiable. We know that. We know that. And its derivative is going to be like this. Correct? So I'm going to use that result. Let me go back to the page. We are here. So based on that theorem, I can either use the theorem or, you know what? Okay, fine, let's do it. Sure, let's do it. So this is equal to 1 over the derivative of the sine function, right? So the derivative, how about we call f to be, here I'm talking about f being, so f of x being sine of x for x and minus pi over 2 pi over 2, right? So that's what I'm talking about here. That's my function f in this context. So f prime of the inverse function sine at the point x, generic point x. Okay? All right, and this is equal to what? And this is equal to what? What's the derivative of sine? What's the derivative of f? F is sine. This is cosine. So this becomes 1 over cosine of sine inverse of x. Okay? Cosine of sine inverse of x. And let's have now an algebraic expression in x. Okay, no transcendental functions anymore, no cosine, no trig functions. So let's have, let's rewrite this as an algebraic expression in x. So we write this quantity, this trig expression, as an algebraic expression in x. You've worked on this you've done this many times in trig class. So as an expression in x. So let's do it quickly then. Let's call sine inverse of x to be an angle. Okay. Let's call sine inverse of x to be some angle. How about theta for an angle? So this becomes cosine of sine inverse of x becomes cosine of theta, right? And if theta is sine inverse of x, what can you say about sine of theta? This means that it's x, right? Based on the inverse function. F inverse of x is y if and only if f of y is x, right? Okay. And where does theta live? Where does theta live? Theta lives in the range of sine inverse, right? Theta is sine inverse of x, so it's an output through the function sine inverse. So so theta lives here. It's between minus pi over 2 pi over 2, correct? So theta lives in minus pi over 2 pi over 2 because it lives in the range of sine. Okay. So theta is between minus pi over 2 pi over 2. Sine theta is x. What do I want? I want cosine theta. What can we say about cosine theta using one of the Pythagorean identities? We know that cosine squared of theta plus sine squared is 1. So cosine squared is equal to 1 minus sine squared of theta. Correct? This is probably the most important identity that you learn in the trig class. Okay, Pythagorean identity. All right, and then that in this context, this means 1 minus the square of sine theta, and what's sine theta is x. So this is x squared then, right? Sine squared theta is the same as a notation for sine theta squared. Sine theta squared becomes the square of x, so x squared. And this means cosine theta is plus or minus the square root of 1 minus x squared. Agree? Agree with me? Here x is certainly between minus 1, 1, right? X certainly is between minus 1, 1 because sine inverse is acting on that. So this is a meaningful thing. And now the question is it plus or minus sine? Well, depends where theta lives. Where does theta live? It lives between minus pi over 2 and pi over 2. And between minus pi over 2, pi over 2, what do you know about cosine? It's positive, right? Again, if you forget these, please either ask me or visit that video. It would be a good refresher. All right, so it's the positive because theta lives here. So let me actually highlight it. Okay, so I'm using this part over here, right? very good. So cosine theta then is this. So let's finish that business. That's equal to square root of 1 minus x squared. And this whole thing, this whole discussion was needed to transition. Make sense? Okay, so we, at the end of the day, we wrote cosine sine inverse of x as an algebraic expression in x. You see, that's the algebraic expression. No more, I don't see anything that has to do with sine and cosine anymore. So what's the derivative of sine inverse then? It's 1 over that guy, which is square root of 1 minus x squared. Okay, so therefore the derivative of sine inverse with respect to x is equal to 1 over square root of 1 minus x squared. And this is for any x between minus 1, 1, right? For any x between minus 1, 1. And certainly, as we said, x is between minus 1, 1 here, because for sine inverse to be meaningful, the input has to be in the domain of the function, and the domain of the function sine inverse is minus 1, 1. Correct? But x cannot be 1 or negative 1, because I'm talking about that guy being downstairs. That guy being downstairs, and that guy being downstairs means I cannot talk about 0, right? And it's 0 when x when x is minus 1, and it's 0 also when x is 1. So I'm gonna throw them away, because otherwise this denominator would be 0, and the function sine inverse is not differentiable at those points. Okay. All right, so that's the next result then. You see the property, this is it. And by the way, absolute value of x less than 1 means x between minus 1, 1. Okay. In a similar fashion, we can show that the derivative of cosine inverse of x is that guy, very closely related, and this is also for the same condition, and I'll spare you the details of the rest. Tangent, right? And so on and so forth. Okay. The last three are not used a lot. Typically people use, the first three. They show up more often than not. Okay, the last three do not. Okay. Example. Differentiate y equals 1 over arc sine. So remember, sine inverse is also called arc sine, and cosine inverse arc cosine, tangent inverse arc tangent, right? So let's do part 1. Okay, let's go. So 1, we want to differentiate this function with respect to x. Well, differentiating this function means differentiating the arc sine function at x to power negative 1, right? This negative 1 has nothing to do with this negative 1. This is a notation for the inverse functions, for the inverse sine function, okay? This is not to power negative 1. This is the notation for, it's just a notation here. This is the inverse sine function. That's the reciprocal, right? And now I'm gonna use that formula that we know, the power rule combined with the chain rule, right? What is it? We get negative 1. So this is power rule combined with chain rule, right? Negative 1 times that guy to power negative 2, correct? Subtract 1 from this, times the derivative of this guy. This is chain rule here. Make sense? So again, I combined the power rule, because of that negative 1, I combined it with the chain rule. All right, what's the derivative of sine inverse of x? We just developed it. This is minus 1 then times sine inverse x to power negative 2. and we just developed this. This was 1 over square root of 1 minus x squared, if I'm not mistaken. Correct? Check. Right, 1 over square root of 1 minus x squared. Okay. Alright, if you would like to keep that negative 2 here, great. If not, let's bring it downstairs. So, and that minus 1 is going to talk to this 1. So minus 1 divided by sine inverse x to power negative to power 2. So sine inverse x squared times square root of 1 minus x squared. Now part 2, we want to differentiate this function. So part 2, we have that f of x is equal to x arc tan of square root of x, and we want to find f prime. Okay, so what we know is, we know this result. I'm gonna actually copy it, and this is for any real number. So I know this result. All right, and let's see how we can make use of it. Remember, arctan is the same as tan inverse. So how can we use that? Same story. Don't forget, this is just this x is just a name, right, for the variable. If you don't like x, go back to star. Okay, I'm gonna differentiate the function f with respect to x, and we're gonna use product rule, right? Product rule. So product rule. To get what? To get the derivative of x, which is 1, times the second function arctan of square root of x, plus x times the derivative with respect to x of arctan, which is tan inverse. Let me just stick with tan inverse here. Tan inverse of square root of x. Okay. And if you call this star, you don't see star here, right? This is not the same star. So, I mean, they're cousins, but they're not the same. So what should we do? Chain rule again, right? Chain rule. So this is arctan, or tan inverse, of square root of x plus x times, I'm gonna call this guy u, and I'm differentiating with respect to x this guy. So I'm gonna differentiate with respect to u this guy, correct, times the derivative of u with respect to x. So what's the deal here? Chain rule. So chain rule, and what do we get? We get that this is equal to arctan square root of x plus x times the derivative of this. Now you see that this is the star, right? So now you see that this guy is the same thing as this guy, right? So now we have this format. So I'm gonna employ this result over here then. Oops, I took this with me. One more time, let me try again. So I want to take all this part. Okay, so I'm using this package now to obtain the derivative with respect to the star, tangent inverse at the star. It's 1 over 1 plus the star squared. And what's the star here? It's the u, right? So it's 1 over 1 plus the star squared, which is u, times the derivative of u with respect to x. And u is how much over here? It's square root of x. So d of the square root of x over over dx. Okay, and don't forget what the u is square root of x. So all in all, you get that this is arctan square root of x plus x divided by 1 plus the square of u, so the square of square root of x, times the derivative of square root of x with respect to x. That's how much? 1 over 2 square root of x. Okay. All right. And what's the square of the square root of x? That's simply x, correct? That's simply x. That's simply x. So this becomes arctan of square root of x plus x divided by 2 square root of x times 1 plus x. Makes sense? I mean, I can still simplify here. Okay, let's do that. Arctan square root of x plus, how much is x divided by square root of x? How much is this? If you multiply upstairs and downstairs by square root of x, this becomes square root of x, right? If you multiply both sides upstairs, if you multiply both upstairs and downstairs by square root of x, it becomes x square root of x divided by the square root of x squared. So x downstairs, with that x, they disappear. You only get square root of x. So this becomes what? Square root of x upstairs over 2, 1 plus x. Correct? So that's the part I replaced with square root of x because of this. Okay. All right. The last part, the last example, we need to find the limit of arctan of 1 over x minus 2. Okay. Remember how arctan is defined? Arctan is defined on all of R, right? With image, with range, and being minus pi over 2, pi over 2. Correct? So this is an inclined axis, and this is not vertical. So let's try again. Hopefully this is vertical this time. Okay, that's not horizontal. One more time. So something like this. Okay, so arctan is, as we said, it has two, if you recall this part, it has two horizontal asymptotes. And these asymptotes are y equals pi over 2 and y equals negative pi over 2. Okay, so the green part is arctan of x. Okay, so for part 1, actually based on this picture, what can we say? Based on this picture, let's derive some conclusions. What can we say about this? The limit as x goes to minus infinity of arctan of x. So when x goes to minus infinity, so x are being here, the function is going to minus pi over 2, right? Minus pi over 2. And the limit as x goes to plus infinity of arctan is equal to what? Now if x is going to plus infinity, the function is going to pi over 2. To the horizontal asymptote pi over 2. Correct? This discussion is going to help me now to solve this. Look. So part 1. If x goes to 2, if x goes to 2 from the right, where does x minus 2 go to? So if x goes to 2 from the right, so which means it's going to 2 while being bigger than 2, right? So this means, so x is being bigger than 2, so this means x minus 2 is positive. This guy is positive, but it's decreasing to 0. Correct? So x minus 2, so if x goes to 2 while being bigger than 2, x minus 2 is going to 0 while being positive, agree? Because x is bigger than 2, so x minus 2 is certainly positive, but it's going to 0. Then what? Then what? What can you say about 1 over x minus 2 then? So maybe a period here. Then, as such, 1 over x minus 2 is going where? So 1 over x minus 2, if x minus 2 is going to 0 plus, 1 over x minus 2 is certainly going to infinity, and to be more precise, it's going to plus infinity, because that entity is always positive. Correct? So that's going to plus infinity. One more time. If the guy downstairs is which is x minus 2 going to 0 from the right, the entity is, the result should be positive for sure, because upstairs positive, downstairs positive, so the result is positive, but it's so small, right? Because downstairs is going to 0. Sorry, it's so big, I should say, because downstairs is so small. That whole thing is gonna blow up then. Okay. All right. So this becomes then, that guy is going to infinity, and where does arc10 go when that input is going to infinity? So again, if you wanna, just to put it in perspective, if you wanna call this limit L now becomes, you can rewrite L as the limit of, what's the favorite letter? A, maybe? Go to what? Go to plus infinity of arc10 of A. Correct? That's what we have. Because if x goes to 2 from the right, at the end of the day, this whole expression is going to plus infinity. I called it A. I call this guy A. So we get this then. And what is that? Isn't it pi over 2? Isn't it pi over 2? Look, limit as x, forget about the name x, call it A or something. Limit of A go to plus infinity, arc10 of that guy, A, that's pi over 2. So this is how much then? That's pi over 2. Okay. So this function has a whole then, 2 comma pi over 2. Okay. All right. Lastly, part 2, integrate between 0 and 1 over 4 that guy. Let me take this down. Okay, so let me use it here. So we want to integrate this piece. And how do we do so? Let me take you to those results. So each differentiation formula has its own integration formula, right? So each differentiation formula is gonna have a corresponding integration formula. And what's the corresponding integration formula for this one? This would be the primitive of 1 over square root of 1 minus x squared dx is equal to sine inverse of x plus a constant, where this constant is an arbitrary real number, right? It's the constant of integration. This would be the corresponding integration formula. How about, I mean, for the second, you can write it on your own. The two most important ones, the two most important integration formulas are the ones that correspond to 1 and 3. For 3, how would you read it? Primitive of 1 over 1 plus x squared dx is equal to tangent inverse of x plus a constant, where this constant is an arbitrary real number. Okay? So in our context, in our problem now, we're gonna need this first one. Okay? So let's go back down. So let me record it. The one we're gonna be needing is the primitive of 1 over square root of 1 minus x squared dx, and this is arcsine of x plus a constant, right? That's the one we're gonna be needing here. Not yet, but that's the one. All right, how can we make it closer to this? And by the way, don't worry about the x again. So let's call this x something else. How about star, as usual? Okay, very good. So now I wanna integrate this guy. I wanna make it closer to this. Who do you think the star is? Who do you think the star is? Well, it's not clear maybe yet, but at least in order to see that this guy as a square, how about writing this 4x squared as 2x, this product squared? So how about writing this one more time? Let me zoom in. How about writing this as the definite integral from 0 to 1/4 dx divided by square root of 1 minus the square of 2x. Okay, how about writing it this way? Well, that highlights what star should be. Star should be 2x, correct? But I don't see star here. This is not star. This is x, not 2x. Well, if you do U-substitution, you get it. If you do U-substitution, you get it. So let's do that. So we're gonna call U, right? So the 2x is gonna be that star. So how about the name U? Is gonna be the 2x, and as such, du is gonna be twice dx, which means half du is dx. Okay, so the typical U substitution, and then this blue part becomes equal to the integral. It's a definite integral. We still need to determine the bounds because we're doing this transformation. Dx is half du divided by the square root of 1 minus u squared, right? Because our u is 2x. Our u is 2x. Okay, so this looks good. I still need to determine the bounds. When x is 0, u is gonna be how much? When x is 0, u is gonna also be 0. So since 0 is a lower bound, the new 0 is gonna also be a lower bound for u. And now when x goes to the upper bound, u is gonna also go to the upper bound. When x is 1/4, u is gonna be 1/2, right? So u is gonna be 1/2. One more time, it's just a simple calculation here. So lower bound goes to lower bound, upper bound goes to upper bound. When x is at the lower bound, u is gonna be at the lower bound. The lower bound for x is 0. That's gonna force the lower bound for u to be 0. And when x reaches its upper bound 1/4, that's gonna be 2 times 1/4, which is a half. 2 times 1/4 is a half. So we get this. And this is equal to what? The half, this constant, times the integral from 0 to half du over square root of 1 minus u squared. Okay, and this is where this property kicks in, because now I see this format, right? This is d star, so d star being the u, du over square root of 1 minus u squared, square root of 1 minus u squared, right? So that's this property then. So this is equal to half. Okay, let me go back to blue. This equals to half times arc sine, or sine inverse, same thing, of u, and this is between 0 and half. Correct? This is a definite integral. I'm not going to worry about the constant. All right, so that's equal to half times sine inverse of half minus sine inverse of 0. Agree? Okay. And what's sine inverse of half? What's sine inverse of half? Well, sine inverse of half is an angle between negative pi over 2 and pi over 2. It's the only angle between minus pi over 2, because sine inverse has range minus pi over 2, right? It's the only guy between minus pi over 2, whose sine is half. So that guy is pi over 6, right? So that guy is pi over 6. That's the only guy that lives in the range of sine, sine inverse, whose sine is half. Okay? And how about this? How about that guy? Sine inverse of 0 is 0, because the only guy between negative pi over 2 and pi over 2 whose sine is 0 is the angle 0. Okay. All right, so we're done with this. So this is equal to 1/2 times pi over 6 minus 0, which is pi over 12. Okay. All right, so this completes this section.